Hello guys, good morning. Good morning to all of you. कैसे हो आप सभी लोग? Just a moment. Is everything all right? Can you hear me properly? Audio is all clear? Is everything all right? Can you hear me properly? Can you start? Today we'll be covering another topic from the atomic physics, and this topic is particularly very important. The topic title is the Zeeman effect. So it's a long topic. It has got several types: normal Zeeman effect, anomalous Zeeman effect, then Passenbach effect. Good morning Ajay. Harry. सब कुछ सही है ना? Everything all right? Okay, so what I was talking about, that this particular topic is a little bit lengthy. It got several types: normal Zeeman effect, anomalous Zeeman effect, and Passenbach effect. In this first part of this lecture, we'll try to cover the first two, and mainly we'll cover normal Zeeman effect today. Then if time permits, we'll go for anomalous, and maybe in the next lecture we'll cover the Passenbach effect. And most of the time questions come from normal Zeeman effect portion only. So without any further ado, let's start today's session. So we'll start with the basic definition of the Zeeman effect. Zeeman, the scientist, in the year 1896, he observed that when a light source giving line spectra, we have seen for, let's say, for hydrogen atom, we have seen line spectrum is observed. We got Balmer series, okay, Paschen series, Brackett series, Zeeman series, and all those series. So the line spectrum. So he observed that when such a line spectrum is placed in an external magnetic field, in that series Zeeman Balmer, we get one line, right? But when it is placed into magnetic field, spectral lines emitted by the atoms of the source are observed to be splitted into number of polarized components. So one component may be divided into three more components under the influence of magnetic field. So if this is the scenario of B equals to 0, and this is, let's say, B not equals to 0. So in simple term, you can understand into number of polarized components. The polarization state of these three lines may be different, or maybe pi, or maybe sigma, sigma plus, sigma minus, and all. In such a way, we'll discuss what are these polarized component later. For fields less than several tenth of 1 Tesla. So what is the amount of magnetic field required to observe Zeeman effect? It is around 1 Tesla or less than 1 Tesla, maybe 1 millitesla also. So in between, maybe 1 millitesla to 1 Tesla. This is the unit of magnetic field, Tesla. The splitting is proportional to the strength of the magnetic field. Strength of the magnetic field has got unit, this Tesla. This effect of magnetic field on the atomic lines is called Zeeman effect. So Zeeman effect is basically the splitting of spectral lines under the influence of magnetic field, in simple language. Now in a singlet spectral line, singlet means S is equals to 0. So what is the multiplicity? 2s plus 1 is equals to 1. A singlet spectral line viewed at right angles to the magnetic field direction. We'll talk about it. We'll draw pictures. You will understand everything. Field spectral line viewed at the right angle to the magnetic field direction. If you apply, let's say, the magnetic field along the z direction, so perpendicular direction or right angles means it is talking about the y axis or y direction or x direction. So these are at right angles, we can say. So if you view right angle to the applied magnetic field, it is observed to be split into three plane polarized components. A central unshifted line, central unshifted line with electric vector vibrating parallel to the magnetic field. This is called pi component. And two other lines equally displaced, means the separation between these two lines will be equally spaced on either side of the electric vector vibrating perpendicular to the magnetic field. These are called sigma components, and this is called a normal triplet. Figure on A will show you the figure, and this is the normal Zeeman effect. Let me show you the figure. This one we have taken from Rajkumar's book. Rajkumar's Atomic and Molecular. Okay, so the fine structure component of the multiplet spectral line, however, shows complex Zeeman pattern. Multiplet spectral line. So when the value of S is not equals to 0, S is equals to 0 means singlet. Now for S not equals to 0, it may be 1, 2, anything. So depending on that, we will get multiple spectra. For multiple spectral line, you will not get only 3 Zeeman components. You will get a complex Zeeman pattern. So those are part of the anomalous Zeeman effect. Okay, when for normal Zeeman effect, you will always get 3 lines. Okay, 3. For anomalous, you may get more than 3. Now, the very famous example of the sodium D lines. Sodium has 2 D lines. One is D1, 5896 angstrom, D2, 5890 angstrom. These two components of sodium yellow light doublet. Doublet, the meaning that it has got 2 lines, D1 and D2. It gives 4 and 6 lines. So for D1 transition, you will get 4 lines. For D2 components, you get 6 lines respectively in the Zeeman pattern. Okay. So you can see any singlet. Singlet means S is equals to 0. Normal, it is eligible for normal Zeeman effect. Remember this thing, normal Zeeman effect requires S is equals to 0, and it is divided into 3 lines, 1 pi 2 sigma. Okay, this is the no field condition, this is the no field condition, and this is the condition under the magnetic field. And this is sodium principal doublet. Here we have multiplet spectral line, and you can see this is the example of anomalous Zeeman effect. Okay, you can see this is the D1 line which get split into 4 lines, 2 pi 2 sigma, and this is the D2 line which is split into 6 lines. Okay, this is known as anomalous Zeeman effect. And this Zeeman effect, the Zeeman splitting is smaller than the fine structure splitting. So I hope you got an overall idea about the Zeeman effect. If anyone has any question, you can ask. DJ has come. If I summarize this effect of Zeeman effect, we can write Zeeman effect is the splitting of spectral lines by a magnetic field. This is a very simple definition of Zeeman effect. When it is done by electric field, that is called a Stark effect. Okay, and it is a configuration of space quantization. Because of space quantization, we see this Zeeman effect. And we have already understood, while understanding vector model and all, what is space quantization. So when an atom is placed in a magnetic field, its spectral lines split into several polarized components, and this splitting is proportional to the strength of the applied field. So we have already discussed it, I have just summarized. Now, depending on the strength of the magnetic field, we got strength of the magnetic field, we got various types. So how Zeeman effect is happening? Zeeman effect is basically the interaction between the magnetic field and the magnetic moment. Okay, so it arises from the interaction between the magnetic field and applied magnetic field. You may get confused because magnetic field also generates internally, and the magnetic moment due to an electron revolving around the nucleus behaves like a dipole. The magnetic moment due to orbital and spin, both orbital and spin angular momentum. We have already derived these things in the previous classes. Now, depending on the strength, we get two types of Zeeman effect. Okay. So, depending on the strength, of the applied magnetic field, we got various types of Zeeman effect. We get number one, weak field effects. Weak field Zeeman effect. For this kind of Zeeman effects, the applied magnetic field is weak, and we get the strong field Zeeman effect. So, weak field Zeeman effect, it may be either normal Zeeman effect or anomalous, normal or anomalous. Zeeman effect. And the strong field Zeeman effect is the Passenbach effect. Passenbach effect. Now, let us try to understand this term, splitting into several polarized components. So, nature of the emitted photons in this case. I hope this is done. Let's move on. Give the heading polarization of the emitted photons. Polarization of the emitted photons. So, if you take an example, let's say we have two levels, which is denoted by, let's say, for the time being, I am saying that they are denoted by their J values. Okay, this is under the condition of B is equals to 0. Okay, plus now when you apply B not equals to 0, so J value will show space quantization. So this one line will be divided into 3 lines, mg value -1 to +1, right? And 0, this is only one line. So this will be +1, 0, -1, and this will be your 0. Now there will be transitions. Delta mg equals to 0 plus -1. So -1 to 0. This and this. So how many lines you get? You get 3 lines. This is the central unshifted line phi. This is sigma plus, this is sigma minus. Okay, these are the mg values. And these splittings will be seen. Now we have used a term that the nature of the emitted photon will be plane polarized or polarized in perpendicular direction depending on in which direction you are observing. So I am just drawing it here. Let's say this is the z direction, this is y, and this is x. X, y, and z. Your magnetic field has been applied along this direction, z cap direction. And this is B. Now, if you observe it in a parallel direction to the applied magnetic field, so how the sigma plus and sigma minus looks like? When you give a direction in the anti-clockwise sense, and when you give the direction, sorry, this is clockwise, this is anti-clockwise. Anti-clockwise is sigma plus, clockwise is sigma minus. Okay, so we can also imagine it in this, in the negative direction of z, along this direction. Okay, anti-clockwise, maybe clockwise. The anti-clockwise sigma plus, clockwise sigma minus. So polarization of the emitted photons. First of all, we'll talk about the longitudinal observation. So longitudinal observation means in the line of the magnetic field. So first case, longitudinal observation. So for longitudinal observation, how many different components you will see? When the emitted photons are observed. When you talk about transition, transition means what? Emission of photons, right? When the emitted photons are observed in the direction of the magnetic field, in the direction of the magnetic field, magnetic fields. You see, we have only shown sigma plus minus, we have not shown pi lines. So when the emitted photons are observed in the direction of the magnetic fields, then the pi lines, the pi line is found to be absent, found to be absent. Only sigma plus minus are present. And which polarization state are there? They are in the circular polarization state. Sigma plus right hand circularly polarized, sigma minus left hand circularly polarized, and both are circularly polarized. If you consider this is right hand circularly polarized, and if you consider this is left hand circularly polarized. Right circular polarized, left circular polarized. Now let's talk about the transverse observation. Transverse means making 90-degree angle. Sigma minus clockwise, yes, sigma plus anti-clockwise. So for transverse observation, what you will see, all three, so we can have pi or you can have sigma plus minus. All three are present and they are all linearly polarized. Okay. So now transverse observation means you are observing it perpendicular to the electric field, sorry, magnetic field. So you will have all linearly polarized component. So in the direction parallel, this will be your pi, and in the perpendicular direction you will have your they are all linearly polarized. Okay, this is sigma plus, this is pi, this is sigma minus. So perpendicular direction to z may be y axis or it may also be x axis, right? So along x axis also it will have, remember this pi component, it will be in the parallel direction. This is for pi, sigma will be perpendicular to this line. Like this. This is sigma plus, this is pi, and this is sigma. So I hope you have now understood the observation longitudinal, transverse, Observation means you are keeping your microscope. Let's say if you are keeping your microscope along the direction of the magnetic field, then you will only see the circularly polarized photons. If you place your microscope in a direction perpendicular to the applied field direction, you will see linearly polarized light. Sorry guys, my cold is coming back. Anyone got any question? I hope everything is all right. Let's move on. We will start discussing normal Zeeman effect. For normal Zeeman effect, to observe normal Zeeman effect, we have to check two conditions. Can you tell me what are the two conditions? If these two conditions are satisfied, we can say that we will have normal Zeeman effect. Can anyone tell me what are the two conditions? We have already told you in today's class itself. What are the conditions? Singlet, that is why the name, they are linearly polarized, and this is the direction of vibration. For sigma, the direction of vibration is this. For pi, so that is why if this pi also was like this, we would have called sigma only. Pi would have we called pi. For pi parallel to the magnetic field, parallel to the magnetic field, pi component. And when it is perpendicular, we call them sigma components. It is the nomenclature. Okay, hey. So the first condition is singlet, vantage, very good. And what is the second condition which is necessary? This is observed between singlet states. That is S is equals to 0, 2s plus 1 is equals to 1. If S is equals to 0, ms is also 0. If S is equals to 0, J is equals to L plus S, that is L. And Mj effectively becomes ML. So we can say that is, it is observed in atoms with no spin. Okay. What is the next condition? Another condition, normal Zeeman effect, it is a weak field effect. Okay. If the magnetic field strength is weak and the atom is having no spin, then only we can have this normal Zeeman effect. And for this normal Zeeman effect, we have the following selection rules. Selection rules for transitions. What are the selection rules? So, you know, here not Mj is not there, S is 0, so J is L, so we can consider ML. So we are writing delta ML equals to 0 plus minus 1. The L components, because of the space quantization, will be split into multiple components, and the transition rule will be decided by this. Delta ML may be either 0 to plus minus 1, but ML equals to 0 to to ml is equals to 0 is not allowed if delta L is equals to 0. So we have already told you, let's say if you have if you have a line, okay, like this, the no fill condition, it will get for a singlet atom, then it will get splitted into 3 lines. One is the central unshifted line, this is the pi line, and we have sigma plus and sigma minus. Now, how you can explain this normal Zeeman effect if you talk about the physical explanation? So what can be the basic reason behind it? Obviously the space quantization, right? So we have seen this earlier also. So we have let's say this orbit of the electron, is orbiting, and it will have its angular momentum like this, angular momentum L, and mu L will be directed in a direction opposite to this. Do you remember or forgot? This is a L and this is the direction of mu L. Now L will precess about the magnetic field. So let's say the magnetic field has been applied along this direction. थोड़ा सा अजीब सा हो गया ये picture, but let's make it less अजीब. Okay, so this is the direction of the magnetic field B, and it is along the z cap direction. So L will precess about the magnetic field direction. In a similar manner, as L is precessing, mu L will also precess. In this way, and here your electron, this is the orbit of the electron. So effective S should be equals to 0. So we see, so if you describe it in terms of quantum theory, what is actually happening? And you have understood this direction of L, it gives various component of LZ, MH cut, MLH cut, you can say. In terms of quantum theory, a polyelectronic atom possesses an orbital angular momentum, let's say L, and orbital magnetic moment mu L with gyromagnetic ratio. We have already derived it. Gyromagnetic ratio, do you remember? It is the ratio of the magnetic dipole moment and the angular momentum. What value we got? What value we got for this? Tell me. You can see direction of mu L and L is opposite. The needness to say this. What is the ratio of mu L by L? This is a very important thing. Gyromagnetic ratio gamma. Tell me the value of this ratio. Harry, Ajay, Vantage Murli. When the atom is placed in a magnetic field, E by 2m, very good, E by 2m. So when the atom is placed in a magnetic field, in an external magnetic field, it is always advisable to mention this term external. External magnetic field, when the atom is placed in an external magnetic field B, say along the z direction, L will be the vector, L will precess L precess, the third person singular number, so precesses around the field direction. Look, once we have done this thing previously also, same thing is getting repeated. We have already told you while discussing that this explanation will be useful in explaining Zeeman effect also, and see, we are explaining the same thing. So I am explaining for the normal Zeeman effect. For anomalous, we can just draw the figure and we can understand. We don't need to write this much every time. Okay, I am just writing this for the normal Zeeman effect. For the anomalous Zeeman effect, we can ignore this ML H cut, where this ML can take values between minus L to plus L. Okay, therefore total of 12 plus 1 values. And this precision is known as, what is the name of this precision? Anyone? What is the name of this precision? What is this precision called? Larmor precision, right? Larmor precision. When it is precessing, it will precess with some angular velocity. Okay. It means that in a magnetic field, a particular L value is split into 12 plus 1 different values. In a magnetic field, each L level is split into 12 plus 1 levels, each characterized by a ml value. Okay. Now we have Larmor's theorem. Using Larmor's theorem, we can connect this angular velocity. What is the angular velocity? The angular velocity of precision is given by, what is the angular velocity? Omega. This is equal. It is the gyromagnetic ratio mu L by L times the applied magnetic field B. So this is E by 2m times B. So what is the interaction energy of such a precision? The interaction energy of such a precision is equal to the product of this angular velocity and the projection of L along the z direction, projection of L along the field direction, that is Lz along the field, that is delta E. Previously it was denoted by one single E. Now delta E is the separation induced between the various components. The magnitude of this will be decided by the product of the orbit, product of the angular velocity and the z component of the angular momentum. So, omega value we have got E by 2m times B, and the value of Lz we know, that is ml h cut. So what is this value? This is, if we write in terms of h cut is equals to h by 2 pi, so EH by 4 pi m into B times ml. So in atomic physics we generally express this kind of thing in terms of the wave number. Okay, so in wave number, you know what is wave number? Wave number, when you want to express in wave number, it is expressed in length inverse. Most of the time it is represented by centimeter inverse. Okay, 1 by lambda. In wave number, the interaction energy is minus delta. It is represented in this way. So this is equals to delta E by h. This is the representation. If you divide by delta E by h, you get this thing minus delta T. So this is equals to, you see h and h is getting cancelled, so you get EB by 4 pi mc times ml. Now you see, since the field B is same for all atoms, is same for, okay, if you're considering one atom, so it is same for all the levels, right? It's same for all levels of a given atom, we can write this term EB by 4 pi mc. Okay, so you can imagine E is constant, 4 pi is constant, m is mass of electron, that is also constant, C is constant, and B is same, so it is also like constant for a particular atom. EB by 4 pi mc, we can consider it to be a quantity, let's say we're calling it L prime. Okay, where this L prime is known as Lorentz unit. L prime is called the Lorentz unit. Lorentz unit. Okay, so therefore we get minus delta T is equals to ml times L prime. Remember, L prime is not related to angular momentum, it is related to something called Lorentz unit. So what is this delta T? Delta T is the change in energy, change in energy for each ml level from the original level, from the original level, and the shift is proportional to, as you can see, it is proportional to B, proportional to the magnetic field B. Okay, and the wave number separation between any two consecutive Zeeman levels, any two consecutive Zeeman levels is, look, ml will be separated by 1 unit, right? So each level is separated by 1 unit, and you see the product of L prime is there. So what is the separation between any two consecutive Zeeman level? Obviously L prime, right? Is this understood? Wave number separation between any two consecutive Zeeman level is L prime, and you see L prime is depending on EB by 4 pi mc, so it is not depending on the value of L. Whatever be the value of L. So as you can see, the Zeeman splitting depends only on the magnetic field strength. Now we will consider an example. So main formula is this: EB by 4 pi mc into ml. When we are considering wave number provision. Let us consider an example. Let us consider the transition, let's say 1D2 to 1P1. Now you see, 1D2 is a line, 1P1 is a line, right? This is 1D2, this is 1P1. So under the no field condition, how many line you will get? You will get only one line, one transition you will observe. So under the no field condition, what will you see? You will see that there is a line like this. Now, because of the space quantization, as you apply the magnetic field, a particular L value is split into various ML values. So for let's say, just a moment, what I am saying. Yes, for 1D2, here the L value is SPD 0, 1, 2. So it will get split into 12 plus 1. That means 5 values. What are those 5 values? Plus 2, plus 1, 0, minus 1, minus 2. Now, if we talk about 1P1, let's say, L value is 1, it will get split into 12 plus 1 means 3 values, means plus 1, 0, minus 1. Clear? So under the no field condition, you can see we will get a single line, and that under the application of the magnetic field will be splitted into how many components? 2, 3, 4, 5, 1, 2, 3. Each level will be characterized. Look, for here, for this, there is only one L value, L equals to 2. But under the influence of the magnetic field, these levels will be created, and each level will be described by a particular ML values, right? Very simple and interesting. Atomic, if you can understand, it is a very easy subject and easy to score. So ML values, you can see it is plus 2, plus 1, 0, minus 1, and minus 2. Here it is plus 1, 0, and minus 1. Now we have the selection rules. Okay, what is the selection rule? I told you selection rule was delta ML is equals to 0 plus minus 1. So when we have delta ML is equals to 0, this will give you 5 lines, and when delta ML is equals to plus minus 1, this will give you sigma lines symmetrically displaced around this pi line. Okay, so look at the transitions. ML equals to 0, अच्छा हम लोगों ने कुछ गलत लिखा है क्या? नहीं. If I take this minus 2 to minus 1, let's say, okay, minus 1 to 0, 0 to 1, okay, so plus 1. Now you take minus 1 to minus 1, 0, plus 1 to plus 1. Okay, so delta ML is equals to 0 here, and next you take, let's say 2 to 1, okay, 1 to 0, and 0 to -1. Okay, so this is the no field condition. Under the application of the magnetic field, you will get, let's say, this is these three components. Look, these three transition corresponding to the same line. So you will not get 9 lines, instead you will get only 3 lines. 0 to 0 is not possible if delta L is equals to 0. So here change in L, you see D and P. What is the change in L? It is 1. So for this case you can write. Okay, note down this. So here how many lines you will get? You will get firstly the central unshifted line I, in addition you will get 2 more lines in this way. This is your pi line, these are the 2 sigma lines. No field, and this is field. So I hope you have understood the normal Zeeman effect. Now this separation between the consecutive Zeeman lines, this separation in terms of wave number is denoted by delta nu bar. It is same, delta nu bar. Okay, now most of the question comes from what is the separation. Okay, we have already calculated the separation, that is L prime. Okay, Lorentz unit L prime EB by 4 pi MC. Now let me give you a very special value for this. If you calculate, if you put down the values of E, pi, N and C, it will take too much time. So I am just giving a short formula. With that formula you can directly put the values. You should remember the value, very simple value. Okay, so the wave number separation, the wave number separation between the consecutive Zeeman levels, we have seen it. It is denoted by delta nu prime, which is equals to the Lorentz unit L prime, that is EB upon 4 pi MC. Now it will be very inconvenient if you put these values and calculate in the examination. That will take a lot of time. So you see, you get a very standard result by putting E is equals to, electronic charge 1.6 10 to the power minus 19 coulomb, and the mass of electron 9.11 10 to the power minus 31 kg, and the value of C, speed of light 3 into 10 to the power 8 meter per second. So we get the value of B, okay, in Tesla. What is Tesla? Tesla is actually, we get B in Tesla is a SI unit. It is Newton per ampere meter. Okay, na? Now you see this particular value, after putting all these, we get delta nu prime is equals to EB by 4 pi MC. So E by 4 pi MC, if you calculate, you will get 46.7 B, and you will get it in terms of meter inverse. Okay. Yeah, there is nine transitions, but you see all these 3 transitions corresponding to a single line. Okay, whether you consider -2 to -1, -1 to 0, or 0 to let's say +1, every time it is like you are getting the same line at same point, 1 1 1. So effectively it is a triplet, but you get it as a single line. Okay, position is same for these 3 transitions, every time 1 1 1, here also 1 1. That is why we get to see 3 lines, but actually here it is composed of 3 different lines. It is composed of 3 lines. This is composed of 3 lines. So your answer will be 3, because they are falling on the same wave number. Okay, Murli. So this formula is very important. Most of the question will be done by this formula. Delta nu bar is equals to EB by 4 pi MC is equals to 46.7 B meter inverse. You must remember this formula, because if you put E 4 pi MC, then that will be very time consuming thing. Now let me tell you another thing which will be helpful in dealing with problems. So you know that nu is equals to C upon lambda. So we can say delta nu is equals to minus C by lambda square times delta lambda. So sometimes wavelength separation is given to you in the question. So in that scenario, what you can do, you can use this formula and we can write, let's say delta nu, delta lambda. So if we talk about the magnitude, we can just ignore the negative sign. So delta nu value, you know, look, delta nu bar, when we talk about wave number, it is nothing but delta nu by C. So when you divide by C, we get the wave number. Delta nu bar is equals to delta nu by C. So it is nothing but lambda square delta nu bar. Try to understand the difference. Is everything clear to everyone? Murli, Vantage, Harry, Ajay, are we ready for taking problems? Look, delta nu bar is equals to EB by 4 pi MC. You just remember, I am not writing another formula, because if you know delta nu bar, you can easily calculate delta nu. If you are given in terms of hertz, so you will write delta nu bar into C, that is delta nu. So sometimes you may get confused whether what is the formula of delta nu and delta nu bar. So I am just telling you because of that, because I personally felt this problem. What is, whether it is EB by 4 pi m or EB by 4 pi MC. That is why I am telling you, just remember one formula, delta nu bar is equals to EB by 4 pi MC. When you require to calculate delta nu, you will just multiply C with it. Okay. Let's go for some problem. Too many blank pages I have kept. Yeah. In an atomic transition 1p to 1s in a magnetic field of 1 Tesla. Look, 1 Tesla means it's a weak magnetic field. Shows Zeeman splitting. Totally, how many equations we can expect from atomic and molecular physics as a whole? Maybe 3 questions, 3 to 4, 15 to 20 numbers, 20 marks you can get atomic. That is huge. Our main challenge remains in part C. Okay, many students make a mistake that what they do, they attempt part C first. Let's say they attempt 12 to 15 questions from part C, and it is observed that they make mistakes, 2-3 mistakes they make, and their number gets drastically reduced. So part C is very dangerous section and very rewarding section as well. So you have to make a balance. For part C, you have to keep an attitude, something that whatever answer I do in part C, you should be 100% confident about them. Max to max one question, one incorrect question you can afford. More than one incorrect question and you are out of the list, you can say. Because when you are making one mistake in part C, you are losing 5 plus 5 by 4. Okay, that's a huge number. That can make you or break you. So while attempting part C, be very much confident. Do this one. Magnetic field value is given, Bohr magneton is given, wavelength corresponding to the transition is given, separation in the Zeeman spectral line. Separation in the Zeeman spectral line in terms of lambda. It is talking about delta lambda. What is delta lambda? Do it. And guys, I am again telling you, complete the test series questions. In the test series, there are a lot of good questions. Complete those questions. You are doing PYQ, that is good, but also try to solve all the test series questions. Test series questions are designed in a very beautiful way, so that your syllabus is also covered and repetitive questions are also covered. Most important topics are also covered. Okay, and the solutions I have tried to provide in a very detailed way. Can you do this problem? Delta lambda, we know the formula already. Delta lambda is equals to lambda square delta nu bar. Lambda square delta nu bar, but you are given mu b. We can express it in terms of mu b. If you do little bit of calculation, lambda square by c into delta nu. Okay, or better if you just put the value of delta nu bar. We know the value of EB by 4 pi mc. Now somehow you need the value of mu b. Mu b is equals to, you know, EH cut by 2m. So EH h by 2 pi. 2 pi means 4 pi m. So EH by 4 pi m we have to somehow put. Okay, so lambda square, let's say E by 4 pi we are writing EH by 4 pi m. If H we have multiplied, so H you have to divide. Okay, so B by HC. Okay, so this is lambda square EH by 4 pi m is mu B into B by HC. Option you are getting very good. Lambda square 250 nanometer, 250 10 to the power minus 9, mu B 9.27 10 to the power minus 24, B is 1 Tesla divided by HC. H is 6.6 10 to the power minus 34, C 3 into 10 to the power 8 meter per second. If you calculate, as I told you, look, don't confuse yourself. Just remember one formula and the other formula you can easily derive, which is derivable in few seconds. Those formula you should not remember. Okay, let's say if some formula requires 2-3 minutes to derive, then in that scenario you can remember. Otherwise, if it is only taken 2-3 steps, don't remember, don't burden yourself. This will give you 3 into 10 to the power minus 12 meter, approximately 0.003 nanometer. Remember one thing, to crack CSIR-NET, even if you don't remember all the formula, you can crack it. Because CSIR-NET does not test your memory, but it tests your analytical skill. How capable you are in analyzing problems. Okay. So don't think negatively if your memory is weak. You just need to cultivate the art of solving problems. Then you can easily crack JRF. Otherwise, you keep on reading, keep on doing everything, it may not be cracked. You should build up an habit to solve problems. Then only it is possible. हमारे पास बहुत जगह था, हमने इतना छोटे जगह पे क्यों लिख दिया इसको? Let's move on to the next question, guys. This one you do. In a normal Zeeman effect experiment, spectral splitting of the line at wavelength 643.8 nanometer corresponding to the transition 5 1D2 to 5 1P1 of cadmium atoms is to be observed. The spectrometer has a resolution of 0.01 nanometer. What does it mean? The minimum magnetic field needed to observe this. Resolution means how capable your instrument is to resolve two closely spaced line. So that value is delta lambda. Okay, do it quickly. Lambda value is also given. Lambda and delta lambda is given. You have to find out B. जल्दी करिए दोस्तों. Do it quickly. Ajay, what are you getting? 0.52 Tesla. Very good. Ajay is getting 0.52 Tesla. So what we have, we know the formula delta lambda is equals to lambda square delta nu bar. Now lambda and delta lambda is given to you. Okay. So delta nu bar, just put the values. We need to calculate B. Okay, minimum magnetic field. So what you can do, delta nu bar is equals to 46.7 B in meter inverse. Okay, so everything will get in SI. What is the value of B? B is equals to delta lambda by lambda square into 46.7. Have you done it in this way? Delta lambda is equals to 0.01 nanometer. Okay, so I am just keeping it in this way. Okay? Nanometer we are writing, and del lambda square is 643.8 nanometer square into 46.7 meter inverse. So what are you getting? Calculate. One nanometer will be cancelled and you will get around 5.166 into 10 to the power minus 10 into 10 to the power 9. So approximately 0.52 Tesla. Yeah, 0.516, approximately 5.2 Tesla. B. Okay, so normal Zeeman effect, all of you have understood. Anomalous Zeeman effect is very similar. What is the difference in anomalous Zeeman effect? Tell me. What is the difference between anomalous and normal Zeeman effect? Tell me the two conditions for observing anomalous Zeeman effect. Anomalous Zeeman effect. Yes, not equals to 0. Very good. Any other condition? here S not equals to 0. Okay, and this is a weak field effect. Okay, S not equals to 0 as well as weak field. If it is strong, then it may be passing back also. Weak field is very necessary, otherwise you cannot decide. Now if I talk about the physical explanation, if S is not equals to 0 means J will not be equals to L, J will be equals to L plus S. In this case, previously we wrote J is equals to L and we got different values of ML, but here as S is not 0, we will get both L and S. So whatever we got for normal Zeeman effect, we got in terms of L, ML. Here we will get in terms of J and MJ. So if I talk about the actual procedure, I am not drawing the electronic the orbit of the electron. We are just showing you in this way that the magnetic field has been applied along the z cap direction. Okay. Now L is applying along this direction and ML will also apply in the same line but in the opposite direction. You can see in this way. This is L and this is mu L, let's say. But in this case, S is also there. Let's say this is the direction of B, Z cap. L, now we have S as well. S is applying along this direction. So its resultant J will act along this direction. This is S and this will be your the tip of L. ओके थोड़ा सा इसको ऊपर करना था. Okay, now let us show the rotation of L. L will precess, not rotate, precess about J. Okay, and this J will precess about the magnetic field direction. Okay, in this way. Now the component of J, okay, you can also imagine the opposite component mu. If that is J, mu J will be in the opposite direction in this way. So if your L is making precision, mu will also making precision. It is like two ends of a rod. If one end of the rod is making precision, another end automatically bound to make precision. Okay, this will also make the precision about this mu J direction. This is mu J, and as J is precessing about B, mu J will also precess about B. My drawing is not perfect, but I think that is sufficient to make you understand what is happening. Both L and S are precessing. It is easier to show the precision of L. Precision of J is hard to show. Okay, so this is the component of J. Now J will have its component along the magnetic field direction, that is Kz. Previously, what ML was responsible for? ML was responsible for splitting of the spectral lines. Here, that thing will be decided by MJZ. Okay, the Z component of J is JZ. So if I talk about, I am not writing. Okay, in the previous one I have written. So here also you can imagine that L and S both precess about J, and under the influence of the magnetic field, J starts precessing about B, and J will have its component because of the space quantization along the magnetic field direction, and that value will be MJ H cut. Okay, the value of JZ along the magnetic field direction will be MJ H cut, where this MJ will have its value between plus J, J minus 1, J minus 2 to 0, 1, 2, sorry, minus 1, minus 2, and so on up to minus J. So in short, if I write minus J, 2 plus J, total 2J plus 1 values. Okay, so each J level breaks up into 2J plus 1 levels. 2J plus 1 level. This is B equals to 0. This is B not equals to 0. Now, if you want to calculate the interaction energy, the way we calculate delta E, here delta E will be separation of the Zeeman component, Zeeman separation, you can say Zeeman separation in terms of the energy unit. Delta E, we have told you, it will be the product of the angular velocity and the Z component. We took LZ in the previous case, here we will be taking JZ. Okay, so omega JZ. Now the value of this omega here, it is little bit different. Okay, what is the value of this omega? E by 2m into B. So here a factor of G will come. कहाँ चला गया? It will be like this. So this is equals to G times mj EH cut by 2m times look you can write this thing in this way. EH cut by 2m you can write mu b G times mg times mu b into b. For anomalous Zeeman effect, S is not equals to 0, and because of that, factor of G will come. Because you see, in the normal Zeeman effect also, G value came. We'll talk about G. Wait a minute. For the timing, we'll come back to it. Why G is there? Just complete this derivation, then we'll talk about it again. So, in terms of wave numbers, in wave numbers, the interaction energy is, if you take the expression of G, you will easily understand why G is there and why G is not there, means G is equals to 1, we can say, for normal Zeeman effect. The interaction energy is, if I let's say minus delta T, this is equals to delta E upon Hc in the previous manner, G times mj into look, we are taking it EH by 4 pi m to keep a balance. To make it like the previous one, we are writing it EB by 4 pi mc. So you can write in terms of mu b, or you can also remember it in terms of this, because in the previous case we have remembered in this way EB by 4 pi mc. We are doing it in this way, not taking up H cut, where EB by 4 pi mc is the Lorentz unit, so G mg L prime. So well, L prime is again EB by 4 pi mc. This is known as the Lorentz unit. Okay. And now you can see previously it was separated by 1 unit. Now the separation is depending on the G value. The Zeeman splitting for different J levels is different, are different. And it depends on the value of G for that level. Now how okay, G value is important. Now this G is identified as Landau factor. We have already given you the expression of Landau factor while discussing vector atom model. Vector atom model, you can imagine how important it is. It's like the base model. Landau factor we have given you. So for a particular level, Landau factor will be decided by this formula: 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2J J plus 1. Okay. Now you see when J is equals to L, means S is 0. J is equals to L, you see G is equals to 1. That is why we get no G for normal Zeeman effect. That is why we got this minus delta T is equals to mg ml L. Here we do not write J, right? We write L, ml L prime in normal Zeeman effect. So we can say in one way that normal Zeeman effect is a special case of anomalous Zeeman effect. In that way you can say. Understood now, Harry? The issue of G. Now it is resolved or not? Tell me quickly. Now sometimes in your examination things may be given in terms of mu b. So you should also remember that formula. Okay. You can easily convert now. EB by 4 pi mc. So you can put it h by EH cut by 2m by multiplying and dividing. You can do it as the way we did in a problem. No? You can do it in that way. Don't unnecessarily increase the amount of formula, number of formulas. Okay, let's move on. Now what about the polarization of the emitted photons? Okay, we have given it for normal or okay, for anomalous. Give you the formula. Okay, here we have only told you what are the polarized component present or absent, and specifically for anomalous Zeeman effect we'll talk about it. Polarization of the emitted photons in anomalous Zeeman effect. Question may come from this. Line is no longer a line, it is becoming a curve. Let's move on. Firstly, with longitudinal observation. What does it mean? We are observing parallel to B. We have kept our microscope or eyes parallel to B. In this case, this transition delta mj is equals to 0. These transitions are absent. Transition are absent. We have told you pi component is absent for parallel to B, longitudinal we told you, and delta mj is equals to plus minus 1. This will give you sigma plus minus circularly polarized light. This will be present, circularly polarized. Okay, when you get delta mj is equals to plus 1, this corresponds to right circularly polarized, and when you get a minus 1, it is corresponding to left circularly polarized. With longitudinal observation, now let's talk about with transverse observation. If you observe in a direction perpendicular to the magnetic field, then what kind of thing will observe? Perpendicular to the magnetic field. In that scenario, we have already told you all the three components will be present. Delta mj is equals to 0. This transition is, these transitions are linearly polarized. Okay, you will see the question, language of the question. In which direction it is observed? Along the direction of magnetic field or perpendicular to it? Only two options, either along the direction of the magnetic field and other two directions in 3 dimension. Transitions are linearly polarized. We have already told you all the three components will be linearly polarized, but delta mz is equals to 0. This will be linearly polarized along the which direction? Tell me. Delta mj is equals to plus minus 1. These transitions are also linearly polarized, but the direction will be different. Linearly polarized, the बताओ. Delta mj is equals to 0. These charges are linearly polarized along which direction? Which axis? Let's say the magnetic field applied along z axis. So along which direction it will be? Harry, Murli, Ajay, Vantage. Tell me quickly. Along, yeah, that is the pi component, but I am talking about the direction. X or y, which one? Delta mj 0 is a pi component. Pi component, you forgot the figure. Look at the figure which I have given you. Look at the figure. X or y, you can say xy plane. Delta mj equals to plus minus 1. That we can say that polarized in xy plane. What about the delta mj equals to 0? Polarized in the xy plane. Perpendicular to B. And delta mj equals to 0. बताओ, in which direction? The direction of polarization will be along which direction? Will it not be along the z axis? Parallel to B. So only one thing, in the first case we have given a general picture. This is the general picture, and specifically we have talked about it. Okay, so along the direction of the magnetic field, no pi component is present, only sigma plus minus circularly polarized present. Along the perpendicular direction to the magnetic field, all the components are linearly polarized. For normal Zeeman effect, you will get 3 components. For anomalous, you can get multiple of this. You can get 3, 4 sigmas, 2, 4 pi's. Okay, it will not be a total of 3. This is particularly for normal. We get 3, but for anomalous, we can get more than 3. In those cases, whatever sigma components you will get, that will be polarized in the xy plane. For the pi components, delta mj equals to 0, those will be polarized along the z direction. I hope everything is now crystal clear. If any question come from Zeeman effect, it should not be missed, guys. And I hope if you have understood everything in the class, you will not miss any question from Zeeman effect. Okay, we are not extending too much, otherwise you will be confused. We'll take the examples of anomalous Zeeman effect on the next class, and we'll also solve a lot of problems. In the next class, mainly we'll be dealing with problems and Passenbach effect. Okay, so we are stopping here. Thank you guys. Thank you very much for joining the session. I hope you have understood each and every bit of it and enjoyed it. Bye bye. Take care. Have a great day. Everybody like this stream. चलिए आज की कार्यक्रम यहीं पे समाप्त करते हैं. आप लोग अपना ध्यान रखिए. चलता हूँ और कई क्लास लेना है मुझे कॉलेज का. चलिए बाय बाय. टेक केयर.